This project focuses on creating modular RGB LED light panels that connect together and are controlled wirelessly through a mobile app. Custom PCBs, a programmed microcontroller, and 3D printed housings allow users to arrange panels in any layout and select colors and lighting effects.
For Legendary Lux, our team's panel design is built around two main parts: a base that holds the PCB and a top cover that snaps on. The PCB is mounted to the base, and the top panel attaches using 3D printed C-clips, so the enclosure can be opened and closed without tools. For light transmission, we use a transparent PETG filament so the LEDs can shine through and create the diffused glow across the surface. This works well for a functional prototype, but it also reveals some limitations of 3D printing. The clips are sensitive to print orientation, so the layer lines can become weak and lead to snapping under repeated use. The transparent PETG also doesn't diffuse light as evenly as a translucent plastic mold, and you can see inside the panel, hurting the aesthetics. For a finalized consumer design, we would move to a molded casing with a proper translucent material and an updated clip design, which would give us better strength, more consistent light diffusion, and a much cleaner appearance. Other future design updates would include mounting holes for the PCB, mounting holes for the base panel to the wall, and guides to help users position the panel on the wall to minimize gaps and spacing issues. On the electrical side, our team also had to make sure the panels were powered safely and reliably. We started by estimating the total current draw of the LEDs and control electronics, then selected a power supply, the Meanwhile LPV 136. It's a 36 volt, 100 watt constant voltage power supply, which gives us enough headroom for animations and future expansion without overstressing the supply. We wired the AC side into a standard plug so the system can be powered from a wall outlet, and then designed the DC distribution so power is routed cleanly to the panels through the PCB's connectors. The idea was to keep the layout simple, modular, and serviceable so panels can be added or removed without rewiring everything. While we figured out the power supply, we worked with the PCB design to make sure trace width and connectors match the expected currents from the LPV 136. That meant checking current capacity and making sure components were properly rated. One issue that arose in testing the panel was overheating of the ESP32 microcontroller. In future iterations, we will test the issue and come up with a solution to prevent the overheating, which will inevitably damage the board in the long run. Another change we will implement in the future for the power side is procuring a smaller power supply. The current size of the power supply is too large and can be cumbersome to have as a product.
The PCB design portion of this project can be broken down into multiple parts. The bottom left are the LEDs, which is what everyone will see when the panel is functioning. In the top right are the connectors that go between boards. In the middle is the ESP32C3 Mini 1, which is the microcontroller to communicate with the LEDs. To the right of that is the USB-C, which is used to program the microcontroller. In the top left is a voltage regulator that goes between the USB-C port and the microcontroller to ensure that the microcontroller does not receive too much voltage. The bottom right is a circuit for our custom power supply. This comprises of an E-fuse, a voltage regulator, an off-mom switch, and a voltage level translator. All of these pieces are laid out into the PCB design shown here. As you can see, the VCC has a thicker trace, which is to compensate for a heavier current supply coming from the power supply. This all comes together into a physical board shown here. On the left is the voltage regulator, E-fuse, off-mom switch, and on the right is the microcontroller, voltage level translator, voltage regulator, and USB-C port.
Here is a presentation of the basic functionality of our wireless modular LED panels. We have two boards, one loaded with the primary firmware and one with the secondary firmware. The primary board is an ESP32 development kit. I'm using this because I only have one custom PCB at the moment. The custom board is running as our secondary. In a production setup, the primary board would be powered by a standard 120 volt wall outlet power supply, and the secondary boards would daisy chain power through connectors on the primary. For this demo, we're using two USB-C cables connected to standard 5 volt wall adapters. When a secondary board powers on for the first time, it enters a pairing mode. indicated by these pulsing blue lights. This tells the user that the board hasn't been assigned an ID yet and isn't connected to the primary's network. To pair a board, we send a command to the primary via Bluetooth containing the secondary's MAC address and the desired board ID number. For this demo, I'm using the NRF Connect app to send Bluetooth commands directly. The goal of the final product is to have a custom app where pairing is as simple as scanning a QR code printed on each board. Once the pairing command is received, the secondary board flashes green to confirm successful pairing. An important feature, secondary boards remember their assigned IDs even after being powered off. So once you've paired the boards, they stay paired. No need to rescan QR codes every time you turn the system on. Now that the board is paired, you can send commands to control the LEDs. The primary board analyzes each command. If it's meant for itself, it executes locally. If it's for a secondary, it relays the command wirelessly via ESP-NOW. We can control individual LEDs on any board, set all LEDs to a specific color and brightness, or activate animation modes like breathing, rainbow, chase, sparkle, or wave effects, each with customizable colors and speeds.
Hello, and welcome to the demonstration of the mobile application portion of the Bluetooth RGB LED panels. To start, we're going to connect our app to the device itself. So we're going to go to Bluetooth controls, and as you can see, it is not connected. And we're going to press scan and connect. It will find the primary board, so we're going to pair it. And to test that it's successfully paired, even though it says connected, it's important to send a test LED, and it will light one of them up as red, and that is how you know there's a successful connection. So, to initialize the board, we're going to press initialize, and it will flash the LEDs white, which shows that it is working properly. So now the user has the option to select individual panels and light them whatever color they would like. So that will send the blue over to those 3 LEDs on the board, and each board has 16 individual LEDs, and the user can also select all and apply color to all of them. The key feature of this app is the panel arrangement tool. So this screen right here represents one board with the 16 individual LEDs. This screen right here will represent each panel as a whole, including all of those individual LEDs. For example, this is panel 1, which would have 16 LEDs on. And the color is just a general representation of whatever is mostly on the board. The purpose of this tool is for users to build and simulate the board arrangements that they would have in their room, such as having P1 as the primary, the one with the ESP32, and all of the sister connections. And this allows them to save designs and even program all of the boards all at once. An example is that we can apply color to each individual board. And then users can have patterns. Fun example of a panel arrangement would be something like this, which would look like fire, for example. And another feature I would like to demonstrate with the color changing that I forgot to mention is that you can not only just use the color wheel, but you can also drag the RGB individually, or the user would prefer to do it this way and have a more precise color scheme. Some more key features are these tools up here, such as the rainbow effect, which will flash all of the LEDs in a rainbow pattern. Another feature we have is the trail effect, which just sends the LEDs in a certain brightness level in a trail. You can change the effect speed, so speed it up. You can also change the effect length. See, it makes more of a longer fade, whereas if you turn it down, it becomes a lot more individual. Another key effect is the pulse effect, which, as you can see, it just makes the entire board pulse from from low brightness to high brightness, and you can change the speed of it as well. So it's really slow, and this is it all the way sped up. One last feature I wanted to demonstrate is that when you are not connected to the board, the app will not let you initialize the panels. So there's a lot of features to know whether or not you're connected to the board or not. But most importantly, once you are connected, you know it will work once you send the test LED.
This project was not completed without a few hiccups, mainly in the areas of price issues and lead times. One of our main goals was to create panels that were more affordable than those on the market. We were unable to achieve this for a couple reasons, one of which being that tariffs added $200 extra alone. In terms of lead times, the PCB had a lead time of a month and a half. This led to rushing in order to get the PCB in on time, as well as an inability to do thorough testing on the other end. The schematic here shows a couple issues that we found when we got the PCB back. Between the USB-C and the microcontroller, there was a low pass filter that was causing data to get lost. We were able to bypass this by shorting the 2 resistors shown in blue and opening the 2 capacitors shown in blue. In the power supply circuit, there was a loop created between the voltage regulator and the E-fuse. This made it so that voltage had to go through the E-fuse in order to turn on the E-fuse. We were unable to bypass this error and had to fall back on using the USB-C as a power supply. Other areas of testing that we had errors was in the app. Due to time constraints, we were unable to get every feature functioning on the app that we were hoping to, as well as some errors when it came between transferring between iOS and Android. The app was programmed on an iOS device, and when transferred over to Android or Windows, we found significant errors in getting it to function.
In conclusion, our project demonstrates a working proof of concept for a modular RGB LED panel system with reliable wireless control through a mobile app. While this first hardware revision doesn't yet support physical panel-to-panel power transfer, each individual panel is operational and able to showcase the lighting features of our design. We've already identified the updates needed for the next revision, and we're confident that the final version would fully support the modular functionality if we were able to implement the changes discussed earlier. Thank you for taking the time to learn about our project.